we will be ready to go. Now, before we get started on the actual math today, a couple of things. Mr. Gerasi on the Birmingham campus, Birmingham West campus, still looking for good folks to participate on the math team. They're having practices every Friday at noon and every Monday at 3 in C100 on the Birmingham West campus. And Darius is here. So if you're interested, if you're going to pursue a little bit further in math, I think you'll find it quite helpful and fun, okay? And it's a good thing to participate in. Now, I did tell, I don't remember if I told y'all or not, but one of the classes yesterday at least, we are having a training 1 week from today, February 22nd, in the afternoon, 2 to 3:45. So that's right in the middle of my office hours, so I just want to let you know I won't be available then during office hours, unless, of course, the training fills up, and then I won't take a seat that somebody else needs, because I'd rather they have the training. Name, please.
Thomas.
Huh?
Thomas.
Coleman?
Thomas.
Thomas, okay, got it. My hearing's so bad. There you are. All right, anyone else come in, Sister Caldwell? So that's coming up next Thursday afternoon. Let me go over a few other things. Normally I have office hours on Tuesdays and Thursdays, like I was saying, at least until first mini-term's over, from 10:45 until 5:15ish or so. I'm not sure I'm going to make it today because, I was exhausted when I got up this morning, and I'm dragging right now. So it may be that after I finish my trig class and maybe make it a little ways into the afternoon, I'm going to give up and go home. So normally I'm on the Birmingham campus, 7:45 to 11:45 on Fridays. I'm pretty sure I won't be there at 7:45 in the morning because I have to go in for lab work at 6:30. And usually it takes them at least an hour to get the labs read and printed out and stuff. And then they've got to contact my doctor and see if he wants me to have treatment. I'm scheduled for treatment tomorrow, but I'm almost certain I'm not going to have it because of the counts I had last time. They shouldn't have even given me treatment last time, I think, because I was already into it before the counts came in. So this time he said, no, I don't have any treatment until he sees the counts, and he'll make a call on that. So I'm pretty sure I won't have treatment, but it's probably going to take them at least, I doubt if they'll contact him before 8 o'clock, and it might be even considerably after 8, and then by the time they get the word back to me and stuff, I doubt if I'll be leaving the Kirkland Clinic before 8:30, okay? And then it'll take me half hour, 45 minutes to get to Birmingham campus, so 9:15, something like that. Hopefully I'll be on the Birmingham campus by then. Now, I do have a meeting at 11, if I'm still able to be there that long, and I'm not receiving treatment, so it's up in the air. But please call, and the number's on my syllabus for the Friday thing. Call before you come. If you were planning to show up, just call first, make sure I'm there, and I don't have a meeting or something like that I will be taken away from. So, just wanted to let you know that. All right, any questions on math? I had some before we came in about the quiz, so I will certainly answer anything to do with the quiz if you've got questions on that. Did you find any? Oh, okay, I thought you were going to find something in the book like it. Okay, again, I'll clarify anything that's on the quiz, help you understand what I was asking, but I won't work a quiz question because that's what I'm going to grade you. But those are very similar to what's in the text. So please get me anything from the text. I'll be glad to do it. Tanisha's here. I know you're on the roll here. There you are. And Brianna is here. Let's see you again. Okay. So no questions All right, if you have questions, please ask them, okay? So, now, I'm going to come back to this slide later. Okay, going to use this slide to do example 5 at the bottom of page 71, section 1.7. We're talking about non-rigid transformations. We had done example 4 and example 5. Now, I've mentioned this, I'm sure, several times, but I want to keep mentioning it. After every example, there is a checkpoint that says audio-video solution is available at larsonprecalculus.com. But some of these examples, this one in particular, or one, for instance, also has at the example. See larsonprecalculus.com for an interactive version of this type of example. Now, not all the ones that are not on the slideshow are like that, but quite often those that they don't show on the slideshow, they do have at larsonprecalculus.com. So you can see and get interactive explanations of that kind of stuff. So let's do, sorry, my voice is leaving me. I'm also exhausted. Compare the graph of each function with this graph. Okay, so let's start off with the graph here. And if I don't remember me telling you before, this book loves graphs. Okay, here's the one we're going to compare to. F of x is equal to 2 minus x cubed. So this is going to be our graph. F of x is equal to 2 minus x cubed. Example 5, bottom of page 71, bottom half of the page. All right. Now, I'm going to set up a graph of my axis here. Okay. I'll tick off a few points here. That means make them mad. And you see my graphs aren't very pretty at all. Okay, now do any of you want to hazard a guess of how to graph the f of x, 2 minus x cubed? You can do it in small bites, or you can just try to attack the whole thing. Anyone make a suggestion? How would you do it? If that was on the quiz or a test, how would you graph that? Please, somebody answer something. All right. How would you approach it? Please approach it. Give it a shot. Anybody? Say something, okay? Say again? What's that?
Could you repeat what you just said?
Okay. If that was, here is the function. F of x is equal to 2 minus x cubed. The thing is, compare the graphs of the things that are following with that. So we've got to graph that function. How would you go about graphing that function? What would be your approach? Let me give you a hint. You're going to have these on the test, okay? So you have one on a quiz. How are you going to approach graphing the function?
Would you pick some x's and then plug in?
Ha! Sounds like a capital idea. Now, do you want to do that in what they call a T-table, or you just like to pick them and go? I don't care. Pick them and go, is that what I heard? Okay. Give me an x. 0, I love it, okay? What is your y, or f of x, when x is equal to 0? Say again? 2, exactly. So x equals 0, y is equal to 2. There we are. We're rolling now. Give me another x. 1. When you put in an x here, f of 1 would equal 1. All right. 1, 1. There's an X. There's a point. Next. 2. What would be f of 2? -6, because 2 cubed is 8. You're subtracting that from 2. That would be -6. There's 1, 2, 3, 4, 5. I can't even quite get down there. So we know we're down here somewhere. Okay? How about another one? -1 sounds like a capital 1 to use. What would be f of -1? Perfect. 3. Right. -1, 3. Right about there. Okay? And if you tried -2, it's going to be way up there, right? So it's going to take off and go here, come down here, flatten out around that one, and head down that way. There's your graph. Good way to do it. Pick points and graph them. Okay? Now, alternative way of doing it would have been to start with the x cubed. You know how that looks. It goes through 1, 1, -1, -1, 0, 1, 1, and goes up. Then you negate it, which flips it this way, which would have it going like that. Okay? And then you add 2 to it, and you got that. So you have this function. This is the flip function moved up by 2. So you could have done it that way, or you could have just picked points and done. You have options, whichever you see best. All right. So we got that part done. Whew. That's just a setup. We're not even into the problem yet. Hardly. Now, the A part of this says, let's compare the graph of that function with g of x, which is f of 2x. So I need a color for g of x. Say again? Need a color. Really hard questions for you today.
Red.
Say again? Red. Okay, we'll go with red. Okay. So here's our g of x. It's f of 2x. Now, what in the world is that one going to do? Hint, we're under the topic non-rigid transformations in hint. What is this going to do? It doesn't flip. That's what negative signs do. Okay? What the 2x does is number one, you're doing something to the x. It's not 2f of x. That would be doing something to the y. This is doing something to the x. Okay? You're doubling the x, which would be a first, which direction? Horizontal. Okay, remember everything you do with x is backward, straight. Okay? Now, what you could do here, and this works quite nicely, for every x you chose before, okay, this is a little tricky. Let's say we chose the 0 before, right? So when you double 0, you still have f of 0, right? And that was 2. So the first one's going to be right smack on top of that one. Okay? Right? Now, the next one, we chose 1 here. Okay? To get this point. If you do 2 times 1, that will be 2. Plug that in up there, and that will be your -8, which is down here, okay? Remember, we went off scale with it, so down here. So now your 1 is way down here, which in effect is a horizontal shrink. You shrunk that horizontally by 1. So we weren't quite on the money here, but somewhere down here is that one. So this one here, to get you the same value you had up here, if you had x equal 1/2, 2 times 1/2 is not that hard. 1, okay? And f of 1 we know is going to be 1. So you see 1/2 then becomes 1. So every x is, you take half of it, you know? So up here, any guesses of where we'll go here? Horizontal. Help me, somebody. Shrink by a factor of, say again? Thought I heard someone whispering. 2. A horizontal shrink by 2. So here you went over to -1 here. Here you'll do -1/2, but have the same y value. Okay? And if you went to 2 up here, 1 here, that would have been the same as 2 up here, which would have been somewhere way up there. So here is your horizontal shrink of that function. So you see, you've made a sandwich out of it. Okay? When you double the x, you have the effect of the x, so to speak. You've compressed it together, a horizontal shrink. Okay. Wow. Okay. Maybe you want to see LarsonPrecalculus.com because it may be helpful to you. Let's do the B part then. I'll need a color for B. Green. Green, green, it's green, they say, on the far side of the hill, okay? This is your h of x, okay? And this h of x is going to be f of 1/2 x. Now, what in the world would that be doing? First, which variable are you messing with? The x. And that's on which axis? Okay, and which one is that? Horizontal or vertical? Second? Which axis is the x on? Horizontal. So this is going to be doing something with horizontal, just like we did before. What do you reckon this is going to do? Number 1, it's a horizontal. Number 2, what's it doing to it? Doubling the x was a shrink. Having the x will be a stretch, exactly. So for every x, you double it because of 1/2, factor of 2. Well, you double 0, you stay 0, okay? You double 1, and you go out here to 2, but at the same value it had for 1. Double the 2 that we had down here somewhere, it goes out to 4, if I can sort of estimate that. Double the -1, it goes over here to minus, it stays at the same level, but it goes to -2 on x, and then it heads off up here. So this time your function is I didn't do that one too well, did I? Is a horizontal stretch. So the green function here is a horizontal stretch. The f value, the y value doesn't change. What you're changing is the x. When you double the x, basically you take half of it. It's a shrink. When you have the x, you double the x. I mean, it's kind of backwards, but it works if you think about it. If you did x equal 2, 1/2 of 2 is? Not that hard. 1, okay? And f of 1 was 1. So you see, now h of 1, h of 2 is the same as f of 1. Okay? That value right there. Okay? So what you've done is a horizontal stretch. Doubling the x is you have the distance you go on x, and having the x, you double the distance you go on x, keeping the same y values you have. Okay? And everything went through the origin, not the origin, but 0, 1, because when you double 0, you get 0. When you have 1, you half zero, you get 0. So they all went to the same point there. All right. Sorry. My voice is fleeing. Okay. Now, I wish I could show the graph, but you'll have to look in your book, and you see it there, and by all means, do a checkpoint. Okay? Go to larsonprecalculus.com to see the interactive version of example 5, and then do the checkpoint for example 5. All right. Now, last time I think we ended before we had a chance to do vocabulary. So let's do vocabulary, top of page 72. In the first 3, we're going to be filling in blanks. Horizontal shifts, vertical shifts, and reflections are blank transformations. Horizontal shifts, vertical shifts, and reflections are what kind of transformations? A little louder. Okay. No, those are the rigid ones. The non-rigid are the others. Okay. So those are rigid transformations. If you flip back to page I want to see where they first mention it. Okay. Top of page 71, the first sentence. Under non-rigid transformation, but it says horizontal shifts, vertical shifts, and reflections are bold print, rigid transformations. Okay? Because the basic shape doesn't change. See, in these, we change the shape. We squished them or stretched them. Okay? In rigid transformation, the shape stays the same, it just moves around, flips over or whatever. Okay, number 2. A reflection in the x-axis, okay, of the graph y is equal to f of x is represented by the function h of x is equal to blank. How do you do a reflection in the x-axis? Something in the air today or something?
Vertical shrink?
Say again?
Vertical shrink?
No, a reflection, remember it's not a shrink or it's a rigid transformation, but the h of x would need to be represented by something. Reflection of the thing in the x-axis. That means if we took, say, this green function here and reflected it about the x-axis, then what would we be doing? It's the negative. It would be the negative of f of x. So h of x would be negative f of x. You've negated the y. Flipped across the x-axis is negating the y. Okay? While a reflection in the y-axis of the graph of y is equal to f of x would be represented by h of x equaling y. Reflecting across the y-axis, what are you negating? It was over here, it goes over here. What is being negated? Y value stays the same. What other value do you have? The x value is negated. So you write that h of x is equal to f of negative x. You negate the x. Flipping across the x-axis, you negate the y, because you were up here, you make it down here. Same x value, but opposite y. So it's minus f of x. If you flip across the y-axis, it's f of negative x. Okay? You're like a dentist this morning. Okay, pulling teeth. A non-rigid transformation of a graph, y is equal to f of x, represented by g of x is equal to c times f of x, is a blank blank when c is greater than 1. Non-rigid transformation of the graph, y is equal to f of x, represented by g of x equal to c times f of x, is a blank blank when c is greater than 1. Vertical what? I couldn't hear it. Stretch or shrink? Stretch, perfect. When c is greater than 1, it's a vertical stretch. Okay? Remember that Y's do exactly what you would expect. Big C's give you stretches, small C's give you strings. Okay? And a blank blank when 0 is less than C is less than 1. In other words, C is less than 1 but still positive. What's that going to be? Same G of X equals C times F of X. So close. Still multiplying by alpha of X, and alpha of X is, what's alpha of X always? Y, and which axis is Y on? Horizontal or vertical? Y? Vertical, okay. So it's going to be a vertical something, and you're multiplying by a small number. Shrink! All right. Do feel like a dentist there. That's a vertical shrink. The other, when C is greater than 1, vertical stretch. C is between 0 and 1, it's a vertical shrink. Okay. Now, number 4. I hope you have your books, because it's hard to pick up all this from just listening to it. Match each H, which is your A, B, C, and D, with the transformation that it represents on the right-hand column, which is little Roman numeral 1, 2, 3, 4, and 4. Okay? Now, what I'm going to do is read you the transformation, and then you tell me which H it is. You have a horizontal shift in F, C units to the right. So H of X is going to be something with F and something with C. What would that be? Horizontal shift of F, C units to the right. Okay. Boy. Does anyone have, a few people have books, okay? Let me go back to a dark color here. Can I go on and erase what's on the screen so it won't be as confusing? Okay? Okay. Let me write down. Let me get my pen back. I thought I did, but I didn't. Okay. Got it. Okay. Here's A, B, C, and D. All right. This is the H of X is equal to F of X plus C. Here the H of X is equal to F of X minus C. Here the H of X is equal to F of X plus C. And here the H of X is equal to F of X minus C. Okay? Roman numeral little I. Horizontal shift of F, C units to the right. Horizontal shift, C units right. Okay? Roman numeral little 2I is vertical shift of F, C units down. Vertical shift of F, I didn't write that in before, C units down. Okay? Little 3I is horizontal shift of F, C units to the left. And Roman numeral little 4 is vertical shift of F, C units up. Okay. Which of those is this one? Okay, you said vertical shift up? All right, that would be Roman numeral 4. How about B? That's vertical shift, C units down, Roman numeral 2. How about H? What left? Yeah, it has to be horizontal. Horizontal shift, left, that would be Roman numeral 3. To the right, that's Roman numeral 1. Does that make sense? Good deal. Got through our vocabulary. Way to go. Homework exercises in. I assigned most of these before. Let me go through them again. Any of the odds, either 5 or 7, or both. They're both at calcchat.com. 9 is at calcchat.com. Either 11 or 13 or both. They're at calcchat.com. And then any of the odds 15 to 19, all of those are at calcchat.com. 15 is at calcview.com. Any of the odds 21 to 37, all of them are at calcchat. 21 is at calcview. Any of the odds 39 to 45, all of them at calcchat. 39 is at calcview. Either 47 or 49 or both. They're both at calcchat. I don't think either one of them are at calccchat. Okay. Any of the odds 51 through 55, they're all at calcchat, none at calcview. Either 57 or 59 or both at calcchat. And then 61 is at calccchat, not calcview. Now, exploration here, they have a few true false, 63 and 65. I assume those are also at calccchat. I haven't looked them up. Good things to think through. Don't expect very many things on quizzes or tests like that, but think through those. The concept will be on the thing. And then 67, 69, 71, any of those, they're all three at calccchat, but none of them are at calcview. Okay? Now, I kind of don't like 69 because it's telling you something wrong, and you have to figure out what's wrong about it. And I just don't like them to ever tell you something wrong, because the wrong part may get fixed in your brain where you really want the right part to be fixed there. All right, let's clear the ink and go back to 1.8. Okay, that's where we're moving next. Any questions on 1.7? Or did anyone come up with a quiz question? Okay, please bring those in if you find them. Okay, 1.8 are combinations of functions, and then something that's kind of new to us, composite functions. Now, you might say, well, combinations of functions are new to me. Well, not as new as you would expect. Basically, when we're talking about combinations of functions, we're going to be adding functions, subtracting functions, multiplying functions, and dividing functions. You've done all that before. Maybe not with functions, but with equations or other things. So you're pretty familiar with that, whether you realize it or not. It's the composite functions are going to be a little bit on the new side, but they're still pretty easy. So, first objectives here, add, subtract, multiply, and divide functions, just like I said. Okay, now, one thing that's going to enter the picture here that you probably haven't fiddled with before is thinking, what does this do to the domain of the resulting function when you add, subtract, multiply, or divide? Because you're doing a function on a function. You're adding two functions together. Well, addition is a function, okay? So what does that do to your domains? Usually we don't worry as much about the range, but we do have to consider the domains. Then we'll find the composition of one function with another function. That's going to be kind of the new part. And we'll use combinations and compositions to model some real life and solve some real life type problems. That's what we love doing, okay? We love it all, okay? So let's look at the arithmetic combinations of functions. And folks, these are just basically what you probably should think they are. It's just adding them, subtracting them, multiplying, or dividing them. There's nothing really all that magical here. Nothing new. Just as two real numbers can be combined by operations of addition, subtraction, multiplying, or dividing to form other real numbers, so two functions can be combined, added, subtracted, multiplied, or divided to make new functions. Okay? So it's combinations of functions. So here's pretty simple. We have the function f of x is 2x minus 3, right? What kind of function is that? Just looking at it, what kind of function is it? I did tell you to forget everything we did last week, right? No, I didn't say that. Okay. What kind of function is this? A linear function, did I hear? Yes. Okay. Because the maximum exponent is a of 1. Okay? It's a linear function, slope of 2, y-intercept of -3. Yes, we know what that is. Here's a g of x. It's x squared minus 1. What kind of function is that? I'm dying up here. What kind of function is this one, g of x? Did I hear quadratic? Probably not, but I'm going to pretend I did. Okay. It's a quadratic function, maximum exponent of 2. Okay? We know what this looks like. That's a straight line, slope of 2. This is what shape do we call a quadratic function? Parabola. Okay? Those sort of U-shaped things. And we can think about this as being, start with your parent function, increase the slope, decrease the, yeah, we can do our transformations on that if we want to. Start with a parent function of the quadratic function and drop it down one. Okay, yeah, well, you can think about it any way you want to. But what happens, or can you combine these two functions to form a sum, a difference, a product, or a quotient? Sure we can. And it's just as simple as what is suggested. If you do f of x plus g of x, it's going to give you a new function, isn't it? Your f of x is 2x minus 3, plus your g of x is x squared minus 1. And when you add those together, what do you get? A little louder? Add those two together. Ever heard of combining by terms? What would that give you? A little louder. X squared. Second. Plus 2x. Minus 4. Yes, you know how to do this. You just combine like terms. Add them together. X squared plus 2x minus 4. Perfect. Now, since they're going to give you the answer, let's us do it ourselves. Do alpha of x minus g of x. How would you do that? I'll open the parentheses for you. I feel very magnanimous today. What would you put next? Maybe the alpha of x. What would that be? Say again? X. 2x minus 3. Close parentheses. Now do the minus sign. X squared minus 1. Now this is just a little more complicated than this one was. Not much. This one you just combine like terms because everything was added. Right? This one, you first have to change signs of this. You really don't change anything here, but you change both signs here. So I would take the time, still, at least until you get really confident of it, right? This is 2x minus 3, and you tell me what to write next. Negative x squared plus 1. Excellent. And now you combine like terms, and what do you get? Negative x squared plus 2x minus what? You may have said it right. I don't hear well. Minus 2. Perfect. Okay. Perfect. You have just subtracted the two functions and come up with a new function, right? That's the difference function. Since we're on such a good roll here, let's do alpha of x times g of x. All right. What do you reckon that one would be? I'll open the parentheses for you.
2x minus 3 close parentheses, open parentheses, x squared minus 1. Perfect. And how do you do that? Second? Yes, exactly. Or the other sort of popular way to say it when they're both binomials is foiling it. Curses, foiled again. Okay? So let's foil it. First, we'll give you 2x cubed. Outer, well, let's do the inner next. Okay? What's the inner? I can't spell foil, by the way. Okay. Minus 3x squared. Now we'll do the outer. I didn't write my 2 down. Second. Minus 2x. And then my last. Second plus 3. Perfect. There we have multiplied the two functions and come up with a new function. And you might not see it, you get a smiley face. And I wasn't very smiley here, but it works. Okay? So there's your product function. Multiply the two functions together. Anyone want to hazard a guess what we would do with a quotient function? The quotient of f and g? What would that be? You tell me. Help me, help me. 2x minus 3 over x squared minus 1. There's your quotient function. Now, there's not much you can do to simplify that. There it is. I mean, can't get too much easier than that, can you? Well, you know there's got to be a little catches somewhere here. Let's go back. What's the domain of this function, f of x? Domain. What values of x could you put in there? All real numbers, okay? How about this one? Help me. G of x. What numbers could you put in? All real numbers. Very good. And when you add them together, guess what you can put in? All real numbers. When you subtract them, what can you put in? All real numbers. When you multiply them, what can you put in? All real numbers. When you combine them, what can you put in? No. Okay. That's the one that catches you. Because what can you never divide by? You see, here's the thing. This function is a polynomial function. Domain's all real numbers. This is a polynomial function. Domain's all real numbers. The sum's a polynomial function. All real numbers. Difference polynomial function. All real numbers. Quotient, product polynomial function. That's not a polynomial function. Why not? You have a variable in the denominator. See, all these variables are in the numerator. They're in the denominator, okay? You could have 3/4. That's no problem, but you can't have an x in the denominator. This one you do. So what must you worry about in a problem like that? Say again? You cannot have a 0 in the denominator. Now express that mathematically for me. Those are great words. How would you say that mathematically? What is your denominator? Say again? Okay, now express it mathematically. What is your denominator there? X squared minus 1 cannot equal 0. There it is mathematically. Isn't that so much easier than writing all those words out? Okay? Mathematicians are lazy, remember? Okay. Now, what would you do with an inequality like that? What's your F word? Oh, please. Factor, of course, okay? And what would you do? Does that factor? Help me? X squared minus 1. Does it factor? How? X. No, you're factoring x squared minus 1. What does it factor as? X minus 1 times. X plus 1. Okay. That product cannot equal 0, right? Now, if the product can't equal 0, that means neither one of these can be 0, right? So what would this mean? That means x minus 1 cannot equal 0. Solve that inequality. How do you do it? Huh?
Plus 1 on both sides?
Yes, add 1 to both sides. Is that what you said?
Yeah.
Yeah, I thought you did. Okay. Add 1, add 1 to both sides. And what does that give you? X equal 1. Oh, no, it cannot equal 1. Okay. And the other one? X plus 1 cannot equal 0. And then what do you do? Subtract 1 from both sides, and that gives you x cannot equal negative 1. Now, before, when those were equal signs, we put an or there. This one, we have to put an and there. It can't be negative 1, and it can't be positive 1, either one of them. So you see your domain changes. Domain changes because it'll be all real numbers, except it can't be negative 1, and it can't be positive 1. But all the other real numbers it can be. I'm jumping way ahead. They're going to get to this later. But that's the only thing you have to keep in mind is what happens when you divide, okay? Now, if that had been an x squared plus 1, would you have worried about it? You certainly maybe worry a little bit and said x squared plus 1 can't equal 0. Well, guess what? You're absolutely right. It never could be 0. Whatever x you put in there, pick an x, is negative or whatever you want it to be. Pick a negative x.
Negative 3.
Negative 3. Square it. Positive 9. Add 1 to it. 10. Is that ever going to be 0? Never. Pick a 0. 0 squared. Plus 1. 1. Is that ever going to be negative? No. Whatever positive number you put there, it's going to be positive if this is a plus number. Remember, it's plus. If it's a negative number you put there, we square it, it becomes positive. Add 1 to it, it's still positive. 0, you square it, it's 0. Add 1 to it, it's 1. Never will you ever have that. So if that was a plus 1 there, no sweat. All real numbers. All real numbers will work. But if you have anything here that could be 0, then you have to exclude those. We did that a few sections ago, right? Okay. So, let's move on, and we'll talk about the same things there, but I wanted you to do the work, not look at them do the work. That's too passive. I wanted you to do active, okay? So when we subtracted the two functions, just like we did, 2x minus 3 is the f, minus the g, which is x squared minus 1. That changes this to a minus, so that gave you minus x squared. That stayed plus 2x. And then this is a minus 3 and a plus 1. That gave you a minus 2. They didn't show all the steps I think they should have. When you multiply the two functions together, just like we did, 2x minus 3 times x squared minus 1, f of x times g of x, then you FOIL it and you get 2x cubed. And then we did the inner next, minus 3x squared, the outer next, minus 2x, and then the last plus 3. There's your product function, a new function. And then this one, you have almost nothing to do. 2x minus 3 divided by x squared plus minus 1. Okay. You should have looked at it and made sure there's no common factors. If there were, then divide those out. There are no common factors, but you have to worry about that denominator. And what we found out, the x squared, x cannot equal either plus or minus 1. All other values will be fine. You just can never divide by 0. Does that make sense? All right, good deal. Let's don't tell me. Oh yeah, there we go. Okay. The domain of an arithmetic combination of functions, that's adding, subtracting, multiplying, or dividing,
functions f and g consist of all the real numbers, the domain of that combination, all the real numbers that are common to both the domains of f and g. Now, the two we looked at were all real numbers, right? But they could have not been. If f would have had some restrictions, like couldn't be 0, or had to be all numbers greater than or equal to 17, or something like that, and g also had some restrictions, whatever they may have been, then you have to take the things that are common to both. This is a place where I tend to think of a number line. Okay? Let's say we have a number line here. Okay? And for some reason our f function either has things in denominators or things in square roots. Remember, those are the things we have to watch out for, right? So let's say that all the values from here to there are good for f. Okay? But g, on the other hand, give me a color. Say again, red? Is that what I heard? Or something else? Red? Okay. Okay. Red, or G, may have been not counting this number, okay, but everything this side of that number. That was the domain of G. Well, then what would be the domain of your sum? That would start here, including this number, and go to here, but not include that. It has to have everything in common. Okay? Now, you won't run into these much, but if all your G's were over here, or your F's are over there, and there's nothing in common, you can't do those operations. It doesn't make any sense to me. Okay? But most of the time, we will have overlap. Sometimes it will be all real numbers. Okay? Other times, we'll have to exclude 2. Okay? Or maybe 7, or a whole half of the number line, or something else. Now, that's for adding, subtracting, and multiplying. It consists of all the real numbers that are common to the domains of f and g. But in case of dividing, you have all those restrictions, plus you have the restriction that g of x can be 0. G of x can be 0 here, adding, subtracting, multiplying, dividing, perfectly good number. But it can't be here because it's a new denominator. So that would often, not always, often give you one more restriction. Okay? So, here is the table that states what we're just talking about. Sum, difference, product, and quotients of functions. Let f of x and g of x, f and g, be two functions with overlapping domains. In other words, they do have some values in common. Then for all the x's common to both domains, okay, the sum, the difference, the product, and the quotient of f and g are defined as follows. Okay? The sum function, f plus g of x, is just take f of x and add g of x to it, just like we did. The difference function of f minus g of x is f of x minus g of x. Boy, pretty simple. The product function, f times g of x, would be f of x times g of x. No thing. Whatever is common to all the domains will work well here. The quotient function would be f divided by g of x, would be f of x divided by g of x. But here you have to restrict the domain a little bit more than this to be also anywhere where x would make that denominator 0. You have to exclude that from the domain as well. Okay? It's the only little bug in the ointment. Okay. So let's do example 1. Given that f of x is equal to 2x plus 1 and g of x is equal to x squared plus 2x minus 1, find f plus g of x. Let me get my dark color back. What is f plus g of x? By that definition we just had, what is it? F of x okay, yeah, but I'm going back to this definition. F plus g of x is f of x plus g of x. And you're doing it right. You don't have to put this stuff in unless you need it to see it.
And now tell me what f of x is. 2x plus 1. Now you could put that in parentheses if you want to. It's not going to help you much. Plus, and what's your g of x? X squared plus 2x minus 1. Because you have nothing in front of the parentheses here, you would just remove it. Because it's only a plus sign in front of this parenthesis, you can remove it. So why write it if you're just going to remove it? Let's just add the two together and what do you get? X squared plus 4x done, right? Because plus 1 minus 1 adds to 0. Okay? So we did this part. Check. Done. Then evaluate the sum when x is equal to 3. So what would be f plus g of 3? What would that be? Okay, it would be plug in the 3. 3 squared. That's a 4 times 3, isn't it? Yeah, we're just plugging in there. And what does this give you? 9 plus 12 is equal to 21. Now, I know what you were saying. I'm going to go back and do it what you were saying. This is also f of 3 plus g of 3. So let's plug those in and see what we get. What is f of 3 up here? It's what? Okay, okay, you go. Okay, go and tell me what f of 3 is. 7. Okay. Now let's use g of 3. This is 7. And g of 3 would be 3 squared plus 2 times 3 minus 1, and that would be a little louder. I can't hear. Okay, 9 plus 6, 15 minus 1 is 14, right? Right? Okay, plus 14, and what does that equal? 21. So it doesn't matter which way you do it. You can either use the f plus g function that you got here, plug in the 3 and it works, or plug in the original f of 3 plus g of 3, that gives you 21. It's the same. Those are equal to each other. Okay? So you see that doesn't matter which way. If it's easier to plug and chug, plug and chug. If it's easier to chug and plug, chug and plug. Whichever you want to do. Either evaluate first and then plug in the values, or plug in the values first and then add them together. Okay? Let's see if we have time. Oh wait, let's erase what we got. Okay, I think that was all of example 1. So let's see what they got. The sum of f and g is just simply f of x plus g of x. That would be 2x minus 1. They like to put them in parentheses. Plus x squared plus 2x minus 1. They like to put that in parentheses. Then the next thing to do, they remove the parentheses, add them together, and you get x squared plus 4x done. Because plus 1 minus 1 is 0. That's the A part. Then when x is equal to 3, just plug that in, and you get 3 squared plus 4 times 3, which would be 9 plus 12 is 21. And they didn't, or do they? No, they didn't show the second part. Okay? How you could just do f of 3 plus g of 3. But y'all saw that at the very beginning, and we're doing it. Okay. Now, obviously, in the slide set, they're going to skip example 2, 3, and 4. Shame on them, okay? And they jump right into composite functions, which we will do next, but we'll first do examples 2, 3, and 4. Do we have time to do any of those today? Maybe not. Sorry about that. It took too long to get things set up this morning. Let me give you a few homework exercises in this section. I'm pretty sure you can do number 3. We haven't really done one like it, but I think you can. And then you can do the A part of 5 through 11, okay? The sum functions. We did the difference in the products and the quotients. Try to do all those, any of the odds 5 through 11. All those odds are at calcchat.com, only 11's at calcview.com, okay? And you can probably do at least number 13, because we did do one like that in class. And that's also at CalcChat and CalcView. And we'll hold off the others. Okay, good deal. Any questions? And please, folks, if you are having difficulty on some of the quiz questions, find problems like it in the text. Homework exercises I gave you that I know you worked at, but just forgot how you did, and bring those to class. I'll work on any of those, so do those. And remember, there's calcchat.com, calcview.com. There's lots of opportunities there. Where do you figure out those over the weekend before you get back to class? All right, and one more thing. Have a good weekend. Working math problems is going to make you good, right? Yes. Okay. What's that? Oh, you didn't get one? Okay. Do you have graph paper? Did anyone else not get a quiz? Some of the people who came in later. Did you have graph paper? Okay, I'll have to run you off some. The copier in the copy room was dead on Tuesday, so I couldn't make copies. Someone did those for me. I'll have to run make some copies of the graph paper. So let's do that. Let me go on and close this down.